Hello, good evening to all of you. So, we'll be shortly starting this session. We'll just wait for 2 minutes so that others can join the session. So, yes, I think, yeah. So, we will be starting with this week 4 session. So, now this live session is based on the lectures in week 4. So, welcome to the course OPAM Practical Application Design Simulation and Implementation week 4. So before coming to the week 4 lectures, I'll just go through the week 3 topics what we learned in week 3. So basically, actually, we learned about clampers like positive clampers and negative clampers and how they behave and what they do. Like we also did a detailed analysis of positive clamper and how these waveforms are derived. And then we moved on to like there were some some issues in the practical clampers also in which I discussed why it is so. Then we also see about the ranges of feedback amplifiers, like it depends on the supply voltage which is given to the op amp and also the gain bandwidth product of the op amp. After that, we also saw different phase shift oscillators. We talked about oscillators, why they are required, and how to implement them. What are the various? What is the first important technique which is used in realizing an oscillator? Then we talked about phase shift oscillator, in which we talked about RC phase shift oscillator, where it adds 180-degree to the output of an inverting amplifier. And then we talked about Wayne bridge oscillators, and then we talked also about LC tank circuit oscillators, which are used for high frequency applications like Hartley oscillators and Colpit oscillators also. So yeah, then we discuss about assignment questions and some extra questions also we discuss. So now we will, after getting a brief overview of what we did in the week 3, now we'll move towards week 4 session. So here, the so in week 4 we talked about comparators and window detectors, positive comparators with positive feedback, inverting Schmitt trigger, non-inverting Schmitt trigger. So step by step we'll look into each and every topic. So first I will be talking about window detectors. So before going to the window detectors, we will see what is a comparator. So just yeah. So this session is recorded, so I will share this video on YouTube also. You can see there also. So yeah, we talk about comparators. Since all these Smith triggers and window detectors are based on comparators, so comparators. So we know that if we simply give V1 and V2 voltages at the input terminals of the op amp, we'll get, since there is no feedback in this op amp, so we'll get some plus minus V set based on the difference of V1 and V2. So V naught is equals to plus V sat if V2 is greater than V1. So V naught equals to minus V sat if V2 is less than V1. So this is how basically a comparator works. Comparator is a easy thing. Based on that, we will be realizing many other things also. So first, we'll move towards window detectors. What are these window detectors? So, as the name suggests, so basically window detectors, as from the name we can say that it is detecting some particular type, some particular part of a signal, input signal. So that is what window means here. So yeah, so if we see the circuit of this, so this is basically made up of inverting comparator and at the same time non-inverting comparator also. Non-inverting comparator. So it is basically a combination of these two combination. And what is an inverting comparator? It is like we are giving input to the negative the inverting terminal of the op amp, and non-inverting means like we are giving input to the non-inverting side of the op amp. So it has two reference voltages, two reference voltage, two reference voltages. One is Vref upper threshold. We can say ut or equals to V ref ut, and another one is V ref ILT, that is lower threshold. Okay, so now how it will work? We'll make the circuit for this. So we will. It is having two op amps, two comparators basically. This is plus. Okay, sorry. Plus minus, and then this is given to the input. This connection goes it here, and then uh, so we have one grounded supply here, and we are giving plus VCC from this rail VCC, and yeah, this is given to this op amp, and this one here. From here this op amp we are taking the output, and there is one load resistor, you can say RL. So these resistors are, so this is the circuit. So this is VCC, since this circuit is acting as a voltage divider circuit. So since we are giving VCC, so each and every point will be having some voltage divided. So here it will be VCC 2 by 3 of VCC at this point, and at this point it will be 1 by 3 VCC. So 2 VCC by 3 is being fed to the non-inverting side of the op amp A1, we can say, and this is op amp A2. So 1 by 3 VCC is given fed to the inverting side of the op amp. So this op amp A1 is acting as non-inverting comparator. Non-inverting comparator, and op amp A2 is acting as inverting inverting comparator. So if we see the working of this type, if we see the working of this window detector, so what is happening? This V1, let's say we gave some input, just like this. So we are like keeping on, we kept on increasing this V in. Okay, so this is V in. So we have 1 by 3 VCC, one reference for the lower threshold, this is lower threshold, and there is upper threshold. Okay, yeah. So then this is 2 by 3 VCC. So if we see the output waveform, how it will be? The output waveform, if we see, huh. So let's go region by region. One, this is region one, this is region two. Then after this, this is region three. Till this, one region, this is another, this is another. Okay. So what we will observe in region one, what will happen in region one? So in region one, we know that V input is less than the lower threshold voltage in this region. So what will happen? This V input. If we talk about A2 amplifier, so then V in is less than 1 by 3 of VCC. So we will be having what, a negative V saturation. But in A1, this V in input is less than 2 VCC by 3. So we will be having plus V sat. So ultimately we will be having V out as 0. So here A1 is having plus V sat, A2 is having minus V sat. So ultimately V out is 0. So we don't get any output there. Okay. After this, if we move to region 2, region 2. So in region 2, I'm talking about this region. Okay. So here the input voltage is more than the lower threshold and it is less than the upper threshold. So what will happen? If we talk about A1 amplifier, the V input is lower than the upper threshold, that is 2 VCC by 3. So the output will be plus VSAT. And in the op amp A2, this our input voltage is higher than the lower threshold. So what will happen? This will be also plus VSAT. This will become plus VSAT. So ultimately we will be having a positive plus VSAT output in this region. So we can say we get a high output. So we can say in A1 this is also plus VSAT output, and A2 output is also plus VSAT. So we got V output as high. Fine. Now if we talk about region 3. In region 3, what is happening? The input voltage is higher than the upper threshold as well as higher than the lower threshold. So that will drive this A1 op amp into plus VSAT mode, and also yeah, no, in A1 op amp what will happen, the input voltage is higher than the upper threshold, so it will drive this op amp into minus VSAT mode. But for A2 it is still the input voltage of the non-inverting side terminal voltage V in is more than the inverting side terminal voltage, that is 1 by 3 VCC, so it will be plus VSAT only. So we will get ultimately V out as 0 here. So A1 will be minus VSAT and A2 will be plus C plus VSAT. So finally we will get V out as 0. So we didn't get anything there in this third region. Okay, similarly we will detect something in this decreasing slope also. Same explanation for this. Then again, no, nothing will be there. So in this way, we saw that this region, this is kind of a window, and that's why we are saying this is a window detector. Okay, so this is plus we said. So this was all about window detectors. So how it is working. Then after this, we move towards op-amp comparators with positive feedbacks. But before going to positive feedback, but why we need this positive feedback in comparators? That is a question. So I'll write the heading for you. Op-amp comparators with positive feedback. So now when we are talking in theory, when we are talking only about theory, then we say okay, we can assume things to be idealistic. But when we talk about real life applications, practical applications, the things are not simple as we as we see that in theory. So what happens? There can be lots of noise also in the input signal. So can it affect this comparator? Can it affect this comparator output? If we see, let's say, as I told you, the operation of the comparator, if this is V1, this is V2. Okay, so you were having this sinusoidal voltage, and it was pure sinusoidal, this input. Okay, this, let's say, some reference was there, and this was V1. So this was reference. So we will get some like if it is more than this, otherwise we'll get something like this. Okay, then it is less. But what will happen if our input is containing some noise, and let's for time being assume the reference voltage to be 0 or the simplicity. So here V ref is 0, it's to 0. So it's like this. Okay, input differential, the input voltage is like this. So if we have some noise here, see, some noise is here, the fluctuations are happening here. So what will happen? The output of the comparator will keep on fluctuating like this at this region, noise region. So this we say 0%. So we were expecting that at zero crossing there will be no noise, and this signal will be smooth. But instead of that, we saw that uh, this is the V reference voltage here. So we saw that at zero crossing, that is like when we set our V reference to zero voltage, then there was some noise. So based on that, if the op amp was like working nicely in this condition, but here it will be having fluctuations because of noise. Again, it will work nicely. Again, at the V reference voltage, it will be fluctuating. Output will be fluctuating. So how to avoid this? So we can avoid this by setting thresholds, setting two thresholds instead of one, and that is being achieved by a positive feedback network. We'll see how we can achieve that. Okay. So we will talk about op amp comparators with positive feedback. Now, so this setting we can change by the way positive feedback. Why we need this? Okay, why we need this? And the answer is because of noise in the input signal waveform that will lead to fluctuations at the output of op amp or comparator, and we saw this like this. Okay, now we will realize op amp comparator is positive feedbacks. So, so I will compare a single reference. I will compare two circuits. If we can say, or I will give you a two study like comparison of two studies, like in which we have one reference voltage and another in which we have two reference voltage, and where the scene of Schmitt triggers and all will come, which comes under this. Okay. So first we have, if we have, let's say we set our reference voltage here, this is V reference, and in idealistic world, if you talk about in idealistic world, ideal case, our input was this V input. So this V input is higher than V ref, so we can say okay, we got our output as higher, that is fine if you wanted a constant DC voltage outside. Yeah, but what if the case is not ideal? We have this reference voltage and we have not like this, but we have some noise in our input signal. So it is like this. So this is V input. Okay. So what will happen at the output in these regions? Since these are crossing V reference, and this is because of noise. We wanted signal like this. We wanted signal like this. Okay, this was what we wanted, but what we are getting here, see, till this point we'll get good signal constant, but then fluctuation will happen. It is crossing the vref, then it will go down, no output will be there, then okay, then again go down, then no then okay, then again it will be zero, output will be zero. So this is the output. So this will be how a practical scenario we will be observing. So then what we can do? Now I will introduce two reference voltages. We now will see can it help in reducing this issues of fluctuations in output. We'll see. So let's say, so I will just give it a heading, introducing two reference voltages, reference voltage levels. So we'll see what will happen. So we have one we have one reference voltage here which will say lower threshold, and another reference voltage which will say upper threshold. Okay. So fluctuation like the comparator will only change its output if the signal goes higher than UT or it goes lower than the lower threshold. So let's say we get a signal V. So signal is like this. So I will just draw the input signal in mental. Let's say like this. So this is input signal. It goes like this. So then it is having some noise is there. Then maybe some fluctuation, some big fluctuations happen, but it is having noise like this. So how our output will be looking like? This is the output. So when it crosses this one, the lower threshold. So till before that it was zero. But once it crosses this and it reaches here, okay, our signal becomes high. Then since there are fluctuations here, but still it will be unaffected by fluctuation because it is not crossing the lower threshold voltage. So lower threshold means basically the output will be low minus V side, and once it crosses upper threshold, it will be the output will be plus V side. So yeah, this is for inverting, non-inverting configuration. So it will be like this. So once again, if some noise, a big fluctuation will come, only then, once it crosses this LT, then only it will be zero. Otherwise, it will not. So we were significantly able to reduce fluctuations in the output. Huh. So that's how by introducing two reference voltages, we can make our system immune to these noises. Now we will see how we can realize this circuit, and yeah, how we can realize this circuit where there are two reference voltages. So first one we'll talk about inverting Schmitt trigger. So we call these circuit as Schmitt triggers, and these are also called as bistable circuits because their outputs are either plus V set or minus V set. So either higher state is there or either lower state is there. So we'll talk about inverting Schmitt triggers. So how it will look like? Hmm. So by the way, I forgot to tell you one thing. So this band which you see here, this band we say noise band because if any signal is between them, then no change of output will be there. Once it crosses the upper threshold or lower threshold, only then it changes will be there. So whatever the noise is there, so this if we increase this band, if we increase this band, this thing, then we can be more immune to noises. So let's say if I give you signal this one reference voltage LT, if I increase this V UT is there. So fluctuations like this, even this big fluctuations are also there. Since my signal once reach the upper cross the upper threshold, then it will remain constant because this noise band is high in this case, large in this case. So we can be more immune to noises, more immune to fluctuations or noises. Okay, so now we're talking about inverting. We'll talk about inverting Schmitt triggers. So I'll draw the circuit for you. Plus, minus, this one. This is output. This is input. The output. Okay. So now we since we were saying that this is a positive feedback comparator, so we have introduced a positive feedback to this normal comparator, and now we'll see how it will function, the functioning of this Schmitt trigger, inverting Schmitt trigger, and why we are saying inverting, that also we'll see. So let's say this voltage is V plus. So what will happen? We will assume, and yeah, so we will assume that uh, one thing we'll have to keep in mind that if V input, this V input is greater than V plus, this V plus, so the inverting side of the op amp is higher than the non-inverting side of the op amp. So our output will be low. V output equals to V low, or it is minus V set. If V input is less than V plus, then V output will be V high plus V set. This is clear, okay? This is easy. This thing. Then how the operation, how it will act? So assume initially V output is high. That is, it is plus V set. We are assuming this. So what will happen, since this is our feedback circuit? So some part of voltage will be here also. It will feed back to the circuit. So V plus will be what? Beta of VH. That is, beta is the feedback factor. So in this configuration, beta is R1 upon R1 plus R2. Okay. So this will be beta VH, which is plus beta VH, which is, we can say, upper threshold. UT. Hmm. So here, if our V in is greater than VUT, so if it is V in is greater than VUT, then what will happen? The output will become low. That is V minus V set, right? That is V plus. If V in becomes less than VUT, then V output is V high. That is plus V set. Okay, so this is one case. Another case is, assume V output is VL, that is minus V set. So then what will happen? So V plus equals to minus beta of VL, that is V lower threshold. So if V in is greater than V lower threshold, what will happen to V naught? So V in voltage is greater than V lower threshold. V lower threshold is here. So it will be high. Now it will be low. Okay. V output will be V low. But in this case, the low voltage, so it will be V low. Okay, that is minus V set. But if it is less than VLT, then V output will become V high, which is plus V set. Keeping these two conditions, 1 and 2, in mind, we can plot the voltage transfer characteristics of this op amp. That is the relation between the output voltage and the input voltage. So we have these thresholds here, that is V lower threshold, V upper threshold. So we observe that when the input voltage is greater than VUT, then it is minus V set. So if it is greater than VUT, then the signal is minus V set. It is here, signal is here. But if it becomes less than VUT, then the signal is plus V set. So our signal will be like this. It will be high, that is plus V set. Okay. And we also saw, so this is the signal. But when our V in is greater than VLT, so what is there? Our signal is negative V set. that is like this. If it is greater than this side, so it will be negative this side. This is minus V side. Okay, but when it is less than VLT, then it becomes higher. So it will be like this. So this is how we observe the VTC, the voltage transfer characteristics of this op amp. Or we'll say Schmitt Trigger, inverting Schmitt Trigger. Now, why we are saying inverting Schmitt Trigger? Because uh, if we give if we give less voltage than the lower threshold, then we are getting the higher output, or we can say we are getting the plus V side. But if we are giving more voltage than upper threshold, then we are getting the negative V side. So that's why it is inverting the input. So that's why we are saying inverting Schmitt Trigger. So after this, we also talked about the positive. Now second comes positive Schmitt, or I will say non-inverting Schmitt Trigger. Non-inverting Schmitt Trigger. Okay. Hmm. So in this case, only the input, like earlier we were giving input to the inverting terminal of this op amp, but now we'll give input to the non-inverting terminal of the op amp. So the circuit will look like this. This is R2, this is R1. Here we are giving V input. Okay, this is grounded. This is plus positive feedback. This is the output. Now if we analyze again, so what will happen? Let's say we are talking about at positive saturation. At positive saturation. V naught equals to plus V sub. That means V naught equals to plus V sub. So then we consider this as V plus. So um, so V naught equals to plus V sub. So if we talk about the what will be this V plus voltage, so then only we can compare. Okay, because anyway we need V plus to be higher than this reference voltage, this the reference voltage which is grounded. This, so then only this will be plus V side. So now we'll see what is the equation of V plus in terms of V. So we use KCL at node A. At node this node A, we can say node A. KCL at node A. And what will happen? We'll see what will happen. So V plus equals to, so we have this V side, this is, we'll get this equation minus VSS minus VIN divided by R1 plus R2 into R1 plus VIN. Okay, if we solve this further, we'll get R1 upon R1 plus R2 V input minus R1 by R2 VSS. Fine. So here we can observe if V in is greater than R1 by R2 VSS, then what will happen? Our out, then V plus will be greater than 0. Then it implies the non-inverting side of the op amp is greater than the inverting side of the op amp. The output will be drive to the plus V side. Okay. So this we can say at the boundary condition when V in equals to R1 by R2 Vs saturation. This is what V UT, upper threshold. So this is what upper threshold. Now if we see the other part when V in this equation itself, or we can say, yeah, in, or we'll see for negative saturation. So at negative saturation. So V output is, we have assumed that is minus V7. So what will happen? Then V plus will be VSS minus VI divided by R1 plus R2 into R1 plus VI. That is VN. VN. Okay. So then after rearranging, we'll get R1 upon R1 plus R2. Then VI plus R1 by R2 VS. So here we see if V input is less than what we say minus R1 by R2 VSS, then what it implies? It implies that V plus will be negative. So here if we see in this circuit, if we input, so V plus will be negative because this is V plus. If this is less than this thing, then this whole thing will become negative. So what will happen then? It will give us the lower threshold limit, which is minus R1 by R2 VSS or minus R1 by R2 V saturation. Okay. So then we can talk also about hysteresis. So hysteresis is what? Hysteresis is simply hysteresis voltage. It is basically the bandwidth of this, like it is the difference between the upper threshold and the lower threshold, or the one which I talked about in this noise band. It is basically the noise band. This noise band I talked about, this is basically the hysteresis voltage. So it will be VH equals to VUT minus VLT, which in this case it will become 2 R1 by R2 Vset. Okay, yeah. And here in this non-inverting Schmitt trigger, beta is R1 by R2. I forgot to tell about hysteresis in this inverting Schmitt trigger. So we'll see hysteresis in inverting Schmitt trigger will be hysteresis will be VUT minus VLT. So that is equals to R1 upon R1 plus R2 2 times into V saturation, where it is 2 beta by V saturation, you can say. Okay, fine. So this we saw inverting Schmitt trigger, non-inverting Schmitt trigger, and then if we talk about the voltage transfer characteristics of with this non-inverting Schmitt trigger, then it will be like V output, this is V input, this is V lower threshold, this is V upper threshold, and since this is non-inverting, so for lower value we'll get lower voltages, and for the values lower than the lower threshold we'll get lower voltages, lower output voltage, that is V minus V set, and for the values for the input voltages greater than upper threshold we'll get high output, that is plus V set. So it is like this. Okay. So this was all about whatever we learned in this week 4 lectures. So we talked about comparators, we talked about window converters, then we talked about inverting Schmitt triggers, then we talked about non-inverting Schmitt triggers. We also talked about why these Schmitt triggers were required, why that two reference voltages were required, two level of reference voltages, that is to reduce the effect of noise and thus if it reduce the effect of fluctuations at the output. Then we'll just discuss about the week 4 assignment questions, like if you had some doubt in that. So then the first question was, what is the purpose of clamp diodes in a comparator? So they were like, so as uh, we can see, we can make the circuit of a clamp diode circuits. It looks like this. So these diodes are connected at the input terminals of this op amp, and if you are giving two signals, let's say this is V1 and another signal is V2. So what will happen if the difference between V1 and V2, V1 minus V2 is greater than 0.7 volts. So either of the diodes will get short or it will get forward bias. So the output will remain the maximum the maximum VD, we can say the differential input we can give to this op amp will be equals to 0.7 volts. Beyond this, we cannot give. So this is used if there is high fluctuation. Let's say there is high fluctuation in one voltage V2, we say, then the circuit may get damage or something. So that's why we use this clamp diode. So accordingly, you can mark the answer for this question. Then the second question was that a comparator can also be classified as depending on the input and reference voltage values. So which of these comparator can be uh, like classified as the based on their input and reference voltage. So we saw like by going through the lectures you can I will not give the answer. You can go through the lectures and you can find easily like which of among these is the called as this. The comparator that can be classified as the depending on the input and reference voltage. So another question was, what is the strategy for getting around the disadvantage of zero crossing detectors? So zero crossing, I told when the signal like here, like at zero crossing, when the signal is crossing the zero, then why then there is some this noise and all those things. So how we remove that? So you can answer this also now. Then the fourth question, that is like identify the comparator that aids in the identification of the unknown input. Hmm. So they are like they are saying the input is unknown, that they don't know the input, and then which is the comparator, which is like among these comparators aids the identification of this. So this also we saw in the lectures. These all are easy questions. Then another question was, pulses of definite width can be obtained from irregular shaped pulses. So like now the first is when it is used as input to pulse transformer or bistable multivibrator or monostable multivibrator or Schmitt Trigger. So this also we see irregular shaped where pulses like when noises are there and all. So which circuit we use, that also you know. So you can answer this. Then Schmitt Trigger is a bistable circuit. So I will just tell that bistable is like two states. The output can be in two forms, like either plus reset or minus reset. It cannot remain in one state. We can make that in one state, but normally it can be work, it can function in two states also. That's what bistable circuit is about. Then based on that you can answer this question. Then there was a question, the voltage regulator has no load output at 18 volts. So they are saying no load output at 18 volts. So no load basically means like no there is no like nothing has been driven from that output. So no current is going through. And a full load output. So when we attach a load on that output of voltage regulator, then there was a fluctuation of the output, that is 17.8 volts. That means whatever the load we attached to that regulator, it was showing a loading effect on the regulator. So that was like because of that the 17.8 volts we get as the output as instead of 18 volts. 18 volts. So based on that, so there is a voltage regulation in these things. From 18 volts, we are getting 17.8 volts. So they are saying now that what is the load regulation. So they are talking about percentage. So we can say like load regulation formula, simple. Load regulation is equals to no load voltage. I will just clearly I will write this. So voltage regulation equals to no load voltage minus the voltage at full load divided by load voltage. Okay, and if we are talking about in percentage terms, based on the percentage of the output current, load current, then we can simply whatever the answer we can divide by the current, full load current. So based on this, you can answer this question also. Now, next question, we'll move to next question. What is the output voltage of the circuit shown below? So by seeing at the circuit, first of all, you will have to realize, okay, whether it is a negative feedback, is it a negative feedback circuit or it is a positive feedback circuit? Because if it is a negative feedback circuit, then we cannot, uh, then we will be going with that virtual short concept and negative feedback concepts and all those things. But since it is a positive feedback circuit, the things will be non-linear. Okay, so we are talking about then a non-linear circuit. So here we saw that this is minus, this is plus. So one thing that is sure that this is a positive feedback circuit, and based on our previous lectures, we can also say that this is a this is a inverting, no, non-inverting Schmitt trigger, because non-inverting Schmitt trigger. The input we have given is to the non-inverting side of the Schmitt trigger of the op amp. So we are giving 3 volts. So what will be the output of this? So since we are giving positive voltage and it is non-inverting, it will show positive results. And basically the output will be high. So based on that you can easily answer this. Hmm. So this is also okay. This question was also easy. Then yeah, another question was there. If ninth question. If the input to the ideal comparator shown in the figure is a sinusoidal wave of 16 volts, so they are saying peak to peak. So it's 16 volt peak to peak without any DC component. So then the output of the comparator has a duty cycle of. So we have to calculate the duty cycle of this output of the op amp. Hmm. So first we will see how the input waveform looks like. This is our input waveform, sinusoidal, and 16 volt is peak to peak. So this is 8 volts, this is minus 8 volts, right? So this is 16 volt peak to peak, peak to peak. Hmm. Then, since it was having no DC component, so so this waveform is like oscillating across DC voltage 0 voltage. So then the output. So now we have a reference voltage of 4 volts. Earlier in our Schmitt trigger case, we were using this reference voltage as 0. The only difference in the question is that it is 4 volts. So now we are getting input from this way, this side. So what will happen? So we have a reference voltage of 4 volts. This is 4 volts. Okay. So something will happen when it crosses this reference voltage. Okay. What will happen? It is based on the which side of this op amp terminal is at high voltage. So we see if it goes high, so this is 4 volts, this line is 4 volts. So if the input signal goes higher than 4 volts, then the non-inverting side of the op amp is having higher voltage than the inverting side of the op amp. So that means the output will driven to the high output stage, that we can say plus VCC or VSS. So whenever it is higher, it will be high, but whenever it is lower, it will be minus VSS. Okay, so only at this region, I'll just mark with the another pen. At this region, it will be high. Otherwise, in this region, it will be low. So this is the situation of a one single wave, one single oscillation of a input signal. So we are getting this. So now they are saying to calculate the duty cycle. So what is duty cycle? Duty cycle is the on period of the waveform divided by the total period of the waveform. So the on period of the waveform, if we consider this T on. So we need T on divided by T. So you can say you need this and this. What will be the time at this T1 and this T2? So you can easily calculate T2 minus T1 divided by total time period. I will just give one more hint that you know the input signal is what? The input equals to peak is what? 8 volts sine omega t. So based on that, you can calculate the values of these points, so this one and this one. And accordingly, you can get T2 minus T. Okay. Now, the last question of this assignment, which is that there is a diode in the feedback. Now, first of all, again, we will see whether it is a negative feedback circuit or a positive feedback circuit. In this case, we can observe that this is a negative feedback circuit. This is minus, this is plus. Okay. Then what will happen? So in the given op-amp circuit, let us suppose that the diode current follows the equation. They have said, they have given that diode current equals to, so whatever the current going from here, it follows this equation. I just e to the power V by Vt. Fine. And they have given Vi equals to 4 volts. V output equals to V naught 1. For 4 volts, it is V naught 1. For Vi equals to 6 volts, it is V naught equals to V naught 1. So find the relationship between V naught 1 and V 2. So they are saying we have to find V naught relationship between V naught and V 2. So what we can do? So we know that since there is a negative feedback op amp, so we can use the virtual short concept here. So this is 0 volts. So this will be also 0 volts this way. So what will be the current flow here? That I will be Vi by 4K. And the same current is going through the diode. So we now know the equation for the current. That is Vi by 4K. Now we have two cases. This is case 1, this is case 2. So based on these cases, we have I1 equals to 4 by 4K and I2 equals to 6 by 4K. If we substitute these two separately in this equation, then what will do? So 4 by 4K Is e to the power. So this will be Vt is the voltage of Vt is the threshold voltage of the diode. Okay, that is not changed. So this is V1 and 6 by 4K Is e to the power V2 by Vt. So now if we also, so this V1 and V2 is the voltage drop across the diode. So this is plus minus V1. So if we see what is the relation between the voltage drop across diode and the V naught output voltage, we can say V diode, let's say the voltage across drop across diode equals to, so if we go like this, that is my V1 equals to minus of V naught, or we can say Vt equals to minus of V naught. That implies V1 equals to minus of V naught, V2 is minus of V naught. So based on this, if we substitute here, if we take log on both sides, okay, then we can get the relation between V1 and V2, or we can get the relation between V01 and V02. Fine. So this is also easy. So we saw what we uh, what we did in week 4. Uh, then we also discuss about the assignment questions. Now I have some extra questions which are really interesting questions, and we will be looking into the applications. We'll be looking into different forms of Schmitt triggers, different applications of Schmitt triggers, window detectors, etc. By these exercises. So it will like give much more deeper understanding of what these Schmitt triggers are and how we can handle these circuits. Okay, so we will go with the first question. So just I'm giving you time to read this question. Just read that. Solutions. Okay, so we'll start. So what is this? First question, what is saying? So design the bistable circuit. So they are saying design the bistable circuit by looking at this figure to obtain, first part is saying to obtain a hysteresis, that we saw that hysteresis voltage they are talking about, that is 2 volt width. So they need a 2 volt width hysteresis, and they are also saying the op amp saturates at plus minus 5 volt. That can be like this is plus 5 volts, the supplies are plus minus 5 volts. Select R1 10 kilo ohms and determine R2. So they are saying, so what value of R1 you will select in order to get 2 volt width of hysteresis. Okay. Now how we will approach? It is simple, as we have seen. First of all, like what type of configuration this is. As we know that, okay, first we saw that which type of feedback this is. So this is a positive feedback. That's why they are asking about bistable circuit. Second thing, now is it a the feedback is there, so there is like Schmitt trigger is this. Then is it a inverting or non-inverting Schmitt trigger? Then this is, since the input is given to the inverting side of the op amp, so then this is a inverting Schmitt trigger. Inverting Schmitt trigger. Okay, so how we will realize this? It is simple, as we know R1 equals to 10 kilo ohm. We need R2. We need R2. We need R2. Okay, and we know plus minus V set equals to 5 volts. Plus minus 5 volts. Fine. Then, so what is the upper threshold of inverting Schmitt trigger? That is beta V saturation, and lower threshold is minus beta V saturation. So what is beta in inverting Schmitt trigger? It is R1 upon R1 plus R2, and this is 5 volts. This is minus R1 upon R1 plus R2. This is 5 volts. So they have also given that the hysteresis of this circuit is 2 volts. Hysteresis width is 2 volts. That is what 2 beta V saturation. Okay. So what is that? 2 equals to 2 R1 upon R1 plus R2 into 5. So from here, if we calculate, so 2 equals to 2 R1 upon R1 plus R2 into 5. Then 2 will get cancelled. R1 plus R2 equals to 5 R1. We get R2 equals to 4 R1. So we know R1, so what will be R2 then? It is 4 into 10k, that is 40 kilo. R2 is 40 kilo. So that's what they asked for. So we designed a circuit which is having a 2 volt width of hysteresis, and op amp saturation voltage is of plus minus 5 volts, and we were given R1 equals to 10 kilo. Easy. Okay. This question was easy. Then moving to the second question. Consider the bistable circuit. Also they are saying that consider the same circuit. This one, and with the op amp's positive input terminal connected to a positive voltage source V through a resistor R3. So now they are changing the circuit, changing the positive or the non-inverting side of the op amp, and now then they are saying then derive the TL and TH circuit. So we know that this this beta is only for this configuration. But what if we have different configuration? That is what being asked in the second question. So first of all, just read the question. Meanwhile, I will draw the circuit for this. Okay. So since they said that a positive input terminal is connected to the positive voltage is connected with a positive voltage source. So we have this. We had this is plus, this is minus. This is from where the uh, input was coming, plus minus. We had this is shorted. Okay, and then we had our feedback circuit. This is V0, this is R1, this is grounded. R2. Now they are saying they have connected a resistor R3 like this in the positive input terminal. In the positive input terminal, this is so here the voltage source is VI, or we can say simply V. VI is this. This is V. Now, so what now? How it will affect the threshold, the limits of thresholds? Like what will be VTL and VTH? So how we will approach this? So as we know, we need in this. Let's assume this is V plus, right? So this is V plus. So if we can get the expression of V plus, then we can say okay how the circuit is behaving. So if we use nodal equation at node A, so using KCL at node A, fine. So what will this be? This will be 0 minus V plus by R1 plus V minus V plus by R3 plus V plus minus V naught by R2 equals to 0. Fine, this is easy. So we are using node 1 for this branch and this branch. Then if we solve, so V plus equals to sorry, V plus into it will be this minus V plus and this will be okay. V plus minus so this will be 1 by uh, minus 1 by R1 minus 1 by R3 plus 1 by R2, okay, which is equals to VR2 minus V naught R3 divided by R3 R2. Fine. Okay, okay. So yeah, so it will be minus plus V naught minus V plus. So this will be plus. This will be VR2 plus V1 R3 V naught R3 V naught R3 by V R3 R2. So V plus will be R3 R2. Yeah. So it will be R3 R2 plus R3 R1 plus R1 R2 divided by R1 R3 R2 equals to V R2 plus V naught R3 divided by R3 R2. Then V plus will be R1 V R2 plus V naught R2 divided by R3 R2 plus R3 R1 plus R1 R2. Okay, so this is like we got an expression of V plus in terms of V voltage and V output voltage. And now, based on this expression, we can decide the upper threshold and the lower threshold for this circuit. So how we can realize if we talk about upper threshold? So the case is upper threshold. Okay. So this is upper threshold. This is lower lower threshold. So for upper threshold, it will be V output will be here in this case it will be plus V7. In lower threshold it will be minus V7. So V plus ut equals to R1 VR2 plus V saturation. So we are substituting V naught as plus V7 in this equation, divided by R3 R2 plus R3 R1 plus R1 R2, and for lower threshold we can get V plus as LT equals to R1, that is VR2 minus V saturation into R2 divided by R3 R2 plus R3 R1 plus R1 R2. Okay. So these are the expression which we got for upper threshold and the lower threshold. Now, yes, what so this is what they ask for, VTL and VTH. So then, what will be the in terms of the web saturation level that we got R1, R2, R3, and R2. So this part is done. Then there is another part which is saying let L plus L this saturation voltage. They said that this is to be 10 volts and V is 15 volts. This V, the voltage which we gave at the non-inverting side, and R1 is 10 ohms. Then also VTL and VTH they have given. So they are saying what will be the values of R2 and R3. So if we say, if we see actually, just add one page in this. Uh, so V plus what they give, V plus is upper threshold voltage what they give as 5.1 equals to R1 or R1 also R1, yeah, R1 they have given as 10 kilovolts. So we must substitute that 10k. So 10k into V they have given as 15 R2, and V set is plus 10, then R2 is there. I think, yeah, this was R2. Okay, then divided by R3 they don't have, they haven't given R3 R2 plus R3 into 10k plus R1 is what, 10k into R2. This is one equation, and another equation is 4 point the lower threshold which they have given like 4.9 equals to, this was upper threshold. So this is lower threshold 4.9. This is 10k. V is 15 volts. This is R2. We have minus 10 into R2, right? And we have R3, R2 plus R3. This is 10k plus 10k R2. So this is second equation. Based on the above two equations, we can get the output as, oh sorry, we can get R2 and R3 as R2 equals to 656. When you will solve this equations, then you can get R2 and R3 as this R2 19.7 kilo. Fine, easy. The main thing was till this point, like finding the upper threshold and the lower threshold voltages. So how you calculated, like basically whatever the circuit is coming, just go with like whatever what will be the expression for V plus, like the expression for the voltage at the non-inverting side of the terminal. If it is an inverting Schmitt trigger, so which is in this case it is. So once you get this expression V plus in terms of whatever parameters are there in this circuit, like V, V naught, Vi, then you can easily solve. Like you can easily decide the threshold, upper threshold and lower threshold of the Schmitt trigger. Fine, this was one question. Then this is the third question. Let's read the question. So here in this question, it is the question that it is saying that consider the bistable circuit in figure 18.22a. So this they are saying this is a bistable circuit. Why they are saying? Because this is a positive feedback circuit. Fine. And with the op-amp's negative input terminal disconnected from ground and connected to a reference voltage. So now they are saying in this circuit they are disconnecting this and they are giving it to a plus V reference voltage VR, that is VR equals to VR. So then they are saying that then what is the expression for the threshold voltages in terms of the saturation levels and the R1 R2 of the circuit. So first we'll make the circuit, like how the circuit will be looking like. So we have the circuit, R1 is here, R2 is here, this is positive terminal, negative terminal, and we have connected our reference voltage VR from this negative input terminal. Then we have our V input. Okay, this is V output. So this circuit you must have seen that this is what positive, or we can say non-inverting Schmitt trigger. But here only difference is that of this VR, V reference voltage. So how we will handle this question? So as I said to you earlier also, if we can somehow, this is V plus voltage, that is the non-inverting side terminal voltage. So if we can somehow get a relation of V plus in terms of this VR, V output and V in, we can easily decide what will be the threshold of this, because based on these two inputs, the input terminals input, the output is being decided. So we'll see how we'll do that. So we'll consider two cases. Case one is when case one, case one. So when the let's circuit is in V naught equals to plus V saturation state, that is the circuit output is high, then what will happen? That means V plus is less than VR. Okay, V plus is less than VR. Sorry, V plus is, by that time V plus is at this position, V plus is greater than VR. But what if we have to switch the circuit to negative V set? So we will have to make V plus less than VR. Okay, this V plus should be less than VR. V plus will be less than. Then only this circuit will become negative saturation. So the boundary condition which we got is V plus V plus equals to VR. So this is where all the things are being decided for this op amp, for this comparator. So this is the boundary condition. So we'll see. So we consider when V plus equals to VR, then only some fluctuation will change. Fluctuation will happen. Either it is from plus V set to minus V set, or minus V set to plus V set. But in this case, we are considering plus V set to minus V set. There will be some change. So for that, we'll use KCL at node A. What is node A? Node A is this. Node A is this. Node A. Okay. So if we use KCL there, that will be VR minus VI divided by R1 plus VR minus VSAT. We are considering the it has just changed from plus VSAT to minus VSAT. Then what is happening? That's why we have said VR, this output is minus VSAT here. Okay, divide by R2 equals to 0. So we'll get VR equals to 1 by R1 plus 1 by R2 equals to V saturation by R2 plus Vi by R1. Then solving it further, we saw VR into 1 plus R1 by R2 minus Vsat R1 by R2 equals to, so we made this equation we wrote this equation in terms of Vi. Okay, so this is Vi. So then since this is, we are talking about negative saturation here, so this will be lower threshold. Lower threshold, which will be VLT will be equal to VR 1 plus R1 by R2 minus V saturation R1 by R2. If we talk about the upper threshold, I'll just add one page here. Add, yes, okay. So if we're talking about upper threshold, then this equation, again if we use that KCL at node A, KCL at node A. So here in this case we are talking about the transition. So initially it was in minus Vset, now it is transitioning to V naught will become plus Vset. So we are talking about plus Vset voltage. So what will happen in this case? V plus will be greater than VR. But again the boundary condition will be V plus equals to VR. This is the boundary condition. This is where the change will happen, boundary condition. So we'll analyze the circuit here itself. Okay, V plus is greater than VR. So you can check the circuit. V plus should be greater than this VR, this negative terminal voltage. So then only this will be at high potential, V output. Okay. So KCL at node A. So how the it will look like this: VR minus VI divided by R1 plus VR plus VZ divided by R2 equals to 0. Fine. Then by uh, yeah, by again solving this equation, we'll get VI equals to VR 1 plus R1 by R2 plus VZ R1 by R2. Okay, which will be VUT, because we consider this for the threshold voltage, upper threshold voltage. So this will be VR 1 plus R1 by R2 plus VSAT R1 by R2. So this is one equation for upper threshold, and this was another equation for lower threshold. So if you will observe this equation closely, then what we'll see that this this part of the circuit, this part of the equation is same as that of the non-inverting Schmitt trigger. Schmitt trigger. But in this case, as this circuit, what was it was telling that it was, as I told, this was non-inverting Schmitt trigger. So by adding this reference voltage, we are getting an extra term here, that is VR into 1 plus R1 by R2. So this is how this extra voltage is deciding the lower threshold limit. So based on this reference voltage, we can change the lower threshold and as well as the upper threshold limits of the circuit. Okay, so when we were considering this VR to be 0, when in this case it was 0, it was grounded, so then this will become 0, this term will become 0, and then we were getting this non-inverting split trigger uh, VI. So that is there. But one interesting thing to observe in this case, like that the hysteresis width, if you'll see, that remains same. That is like 2 VSAT R1 by R2, because this term will get cancelled. When we'll get take the difference of ut minus this one, LT. Okay, so this is there. So now we'll go to the next question. That is question 4. Yeah, just read the question. So in the question, it is written that for the circuit in figure this P18.34, sketch and label the transfer characteristics. So they are asking us to get the transfer characteristics of between V naught and the output voltage and the input voltage. So here they have used two diodes. The diodes are used assumed to have a constant 0.7 volt drop when conducting, and the op amp saturates at plus minus 12 volts, and they are also asking for the maximum diode current. So we are being given input voltage from this side, as by the configuration we can say this is what inverting Schmitt trigger. Inverting Schmitt trigger. Okay. So how this circuit will be behaving and why these diodes are there. So if we analyze this circuit, I'll just read out this circuit and oh, I think yeah, without redrawing, we'll say. So just consider this to be V naught OA. V naught OA. Some voltage, this is V naught as given in the question. Okay. So again we will consider two cases. Let's say when so till this point this circuit is inverting Schmitt Trigger. So we know when V naught A, the V naught A, the output of the op amp is plus V sat. Then what will happen? The V plus will be beta times of V naught. Simple, and beta is what in this inverting Schmitt Trigger case? R1 upon R1 plus R2. V sat. So this is here V set is what? Point R. So now, sorry, this is V output. So because we were looking at whatever the, because initially when we were seeing the inverting Schmitt Trigger case, this V naught was equals to plus V set, and we were saying this was equal to plus V set. This is V set. This was V set in earlier cases, but now it will not be like this in this case. So this V naught. So we need an equation for V naught. So what is V naught? If we look at these things, so since this thing is like V naught A is positive V set, that means diode, if we say this is diode D1 and this is D2, so D1 will be conducting, this will be forward bias. That means V naught will become zero point 0.7 volt. So that is what we can substitute here. V plus equals to R1 upon R1 plus R2 into zero point 0.7. Fine. Similarly, if we talk about when V naught A is minus V set, then what will happen? V plus is given by minus beta of V naught. But what will be beta here? So when the output is negative, so then D2 will be conducting. D2 will be forward biased and D1 will be reverse biased. Okay. D2 will be, in this case it was reverse biased. So in this case it will be opposite of this, the previous case. So then again V2 will be 0.7 volts. So V plus will become minus of R1 by R1 plus R2 into 0.7 volts. So this will be 0.1 volt minus plus 0.1 volt. Fine. So now if we talk about the hysteresis of this circuit, that is what 2 beta by V naught, which we got 2, that is like what is it? So it will be like 0.1 minus or minus 0.1, it will be 0.2 volts. Okay, the transfer characteristics will be looking like this. So this is the transfer characteristics. So we have the limits as 0.1, this is minus 0.1, this is 0.7 volts, the output, maximum output it can go only till 0.7 volts because it is being limited by the diode. This is minus 0.7 volts. Okay, this is upper threshold, this is lower threshold. Since this is inverting Schmitt Trigger, so for the lower it will go high and for the high it will go low, like this. Okay, so this we saw. Now again, now they are asking for what will be the maximum diode current. So if we see the maximum diode current, what it can be, the maximum diode current, we can analyze the circuit at the output terminal. So we have 60K. This is the feedback resistor which we are giving. This is the 10K is, this is the output of the op amp VOA. This is the output of the circuit V naught. And if we are talking about plus V set condition, then diode 1 will be reverse bias, forward bias. So this will be forward bias, that is 0.7 volts. And this second diode will be open. Fine. And this is what V plus, because this is the feedback circuit. From here it is the feedback circuit coming from. So if we say this is I1, this is I2, and current going here it is I3. So I3 will be I1 plus I2. So what will be I1? I1 will be V plus minus V naught by 60k, and this I2 will be VOA minus V naught by 10k. Okay. So then ours, so we can, when if we can substitute this, because we are talking about plus V set, if we are talking about plus V set, then wait. So then what will happen? This plus V set will be zero point 0.1 volt, because we are so we are considering the upper threshold voltage. This one, this condition. So that will be zero point 0.1 volt minus what will be output is 0.7 divided by 60k plus V naught A is what? V naught A is saturated voltage 12 minus, then V naught is 0.7 again by 10k. So this will be 1.12 milliampere. If you will analyze with the on like with respect to the negative saturation voltage, then also this will be the maximum voltage a diode can handle. A diode is the maximum current going from the diode, 1.12 milliamperes I3. Fine. So this was about this circuit. So we what we saw here, we saw here that D1 and D2, what they are doing, they are first of all limiting the output. They are limiting the output to their reverse bias voltages, that is zero point 0.7 volt and minus zero point 0.7 volts. And also at the same time, they are maintaining two reference voltages, two threshold voltages also, zero point 0.1 volt and minus zero point 0.1 volt. So this circuit can be used as a the circuit in which we have to limit the output. Okay, till zero point 0.7 volt and minus zero point 0.7 volts. So yeah. So we'll move towards the next question. So next question is a extension of this question only. So what they are saying in this question, like they are saying, let's eliminate the R1 and short circuit the R2. Then sketch the transfer characteristics of V0 and V1. They are saying assume the diodes have a constant 0.7 volt drop in conducting, and the op amp saturates at plus minus 12 volts. So how the circuit will look like in this case? So it will be like this. So we are eliminating R1 and we are short circuiting R2. So R2 was feedback and R1 was in the input terminal of this op amp. So uh, here it is this resistor is still there, 10k. This is one diode is here and another diode is here, V0. This is VOA. So this is V0. So this circuit is looking like this. So again, if we analyze this circuit, case 1, if V output is, we say plus V set, or we say VOA is plus V set, then what will happen? This is D1 diode, this is D2 diode. So that means V0 will be zero point 0.7 volts, because D1 is forward bias and D2 is reverse biased. Same analysis we are doing which we did in this previous question. This question. Fine. So now V naught equals to plus V set. So V naught equals to 0.7 volts, and D1 diode is forward biased and D2 diode is reverse biased. Then if we say VOA, and if we have to calculate, one case, and the second case is if V naught A equals to minus V set, then what will happen? V naught will be minus 0.7 volts, because D2 will be reverse biased and D1 will be forward biased. Sorry, D2 will be forward biased and D1 will be reverse biased. So V0 will be minus 0.7 volts. So what will be the transfer characteristics? So it will be here in this case, since there is no feedback resistors involved, so the hysteresis width there will be like hysteresis width based on the diodes involved. So here it is 0.7, there it is minus 0.7 volts. So the circuit will look like this. This is 0.7 volts, V output is this, V input is this. This is minus 0.7 volts. This is what 0.7 volts. This is what minus 0.7 volts. Why? Because if Vi if Vi becomes more than, since this is an inverting terminal also, so for high it will be low and this. So for high upper threshold voltage, so if Vi is higher than 0.7 volts, so this will become this VOA will become negative. So that's why it will be going down. But if that it is lower than this minus 0.7 volts, what will happen? So it will be like the circuit will become the output of the circuit will be plus V side. So it will be like this. So what is happening actually? This the reverse bias voltages of D1 and D2 are being fed back to the op amp by a positive feedback circuit. That's what decide. That's what the hysteresis width is being dependent on in this case. So earlier we saw that resistors are used to decide this hysteresis width, but here in this circuit we also saw that by simple combination of these diode also we can maintain this hysteresis width for a circuit. Okay, so this was the extension of the previous question 5. Fine. Then we will move towards the next question. So here it is saying again consider a bistable circuit. So they are saying non-inverting transfer characteristics are there, okay, and they have given op amp saturation voltages also, threshold limits also they have given. So now they are saying they have given a 0.45 volt amplitude sine wave input having zero average. So what is the output? So if you remember, I told you like when we have two reference voltages. So here we have one threshold, one lower threshold. One lower threshold we have that is minus 1 volt, and one upper threshold we have that is 1 volt. Okay. Now they are saying we have a sinusoidal input waveform. Our input waveform looks like this. This is 0.5 volts by peak amplitude. This is minus 0.5 volts. Okay, so now it is having that zero average, so that means its DC is lying at zero voltage. The DC value is lying at zero. So what will happen if we consider this is 0 volt? The sinusoidal waveform will be this, the input waveform. So this is 0.5 volts. This is minus 0.5 volts. So what you can observe from here, we have our upper threshold as 1 volt, lower threshold as minus 1 volt. But the signal which we have inputted to the inverter, a non-inverting Schmitt Trigger, it is in between these two thresholds. That is, it is in noise band. So once the signal is in noise band, nothing. So it is immune to the signals fluctuating in noise band, as we saw earlier also. So that means whatever the initial stage of the comparator was at the moment of the starting, that same stage it will maintain that same stage. So either if it was at high plus we said, then it will remain this constant DC. If it was at negative state initially, then it will remain there. Okay, so this will be the output voltage, no fluctuations in output voltage because signal is less than the threshold limits. So this is a nice intuitive way to see how this noise band behaves in a Schmitt trigger. Fine. Then we have another part of this. So it is saying describe the output if a sinusoid of frequency f and amplitude 1.1 volt is applied at the input. Now instead of 0.45 volt amplitude, they are saying 1 volt amplitude signal is being given to the input side. Then by how, and they are also saying that by how much can the average of the sinusoidal input shifts so that the output becomes a constant value. So they need a constant value at the output, but they all. So let's analyze how the circuit, how the waveforms are looking. So we have, let's say this is 0 volts. We have our lower threshold at minus 1 volt. This is VLT. We have our upper threshold at 1 volt, that is VUT, and our input signal is like this. So based on the previous input signal, if you see this input signal, it was completely lying in this noise band. But if you observe this input signal, there is some part of this signal which is coming out of this noise band. So this is the noise band. Fine. This is the noise band. So this is zero point 0.1 volt extra. So this is 1.1 volt minus 1.1. This is 1.1 volt. So this is 0.1 volt extra. So now the question is saying we need to shift, can the average of the sinusoidal input shift before the output becomes a constant value. So we, in this case, what will be the output if we give this to the comparator? We know once it goes above the upper threshold, then it will become high, otherwise it will be low. Okay, and once it goes, it will be zero, sorry. Once it goes below the lower threshold, then it will be like this. It will be, since this is a non-inverting transfer characteristics, for upper threshold, if it is crossing upper threshold, then it will be like positive. But if it is crossing, so till here it was fine, it crossed here, so till here it was like this. Then this negative voltage will come till that when it approaches, it crosses the upper threshold, till then it will be negative V set. So this is plus V set, this is minus V set. But in the question they are saying they need the constant output voltage. So what we can do, if we can shift this circuit up by zero point 0.1 volt, can this uh, can this remove this thing from here? We'll see. Let's say this was 0 volts, this was VUT, this is VLT minus 0.1 volt, this is 0. Sorry, 1.1 volt. Yeah, this is minus 1 volt, this is plus 1 volt. If we shift the circuit like this, so we are basically shifting the circuit by zero point 0.1 volts upwards. So this will be 0.02 volts, and this will be just touching this. Now this will not be 0 volts, then it will be the middle part of this waveform will be 1. This will be 0.1 volt. Getting? So we have shifted the signal. Uh, we have shifted this input signal so that the it is not crossing the lower threshold. So then how it will behave? So once it crosses the upper threshold, so for the next time it is not crossing the lower threshold, then it will remain constant. So we can achieve a constant DC voltage. So by mainly by just by shifting the input voltage with zero point 0.1 volt, we have changed, based on that we have removed the fluctuations like this fluctuation from the output. So this is what they were saying. So describe the output of a sinusoid of a frequency f and amplitude of 1.1 volt is applied to the input. By how much can the average of the sinusoidal input shift before the output becomes a constant value? So we made constant value by shifting it by zero point 0.1 volts upwards. Upwards. Okay. This was circuit. Now this is also a very interesting question. So in this question, they are saying that they have to design it. Even in the lectures also, like you saw how comparators work. You saw even an application of the comparator, like glowing of LEDs. But then the thing is, in this case, you have to control a thermistor by using this comparators. So how you will do that? So this is an application of comparator. Application of comparators. So they have given that the characteristics of thermistor is given by this, the resistance characteristics. T is the absolute temperature, T naught is some reference temperature, and B is some constant. These parameters are in Kelvin, the temperature parameters. So they need 339 type. So this is basically LM339. These are they talking about LM339 type. Uh, op amp, and the thermistor is having a resistance of 100 kilo ohm at 25 degrees Celsius, that is you can say room temperature, and B is 4000 Kelvin. So they have said design a bridge comparator. So this is important. Design a bridge comparator circuit that gives V naught equals to V naught VOH for T greater than 100 degrees Celsius, and V naught equals to VOL for T less than 100 degrees Celsius. And they are also saying assume 10% component tolerances and they need calibration. So before this we'll just focus on how we can realize this circuit. So first of all they need some bridge comparators, and 339 type, LM just for the help I can say 339 type. I will draw the circuit for this 339 type. So how it looks like, it looks like this with a bridge comparator, plus minus. We have a resistor here R4. There it is. It is given a supply VCC. VCC here. This is V0. This is R5. R3. This is R2. Okay, this is grounded. So we have made this bridge here where our thermistor resistor is here, RT. So this resistor is basically depending on the temperature. That is what thermistor is about. And this is some R1 resistor. So now we have to connect this point and this point at the one of the terminals of the op amp so that we can get the output. Fine. So which terminal should we connect to which terminal of the op amp? So let's say if we connect this to the positive side and this to the negative terminal. So we'll observe what will happen. So this is the voltage VT across the thermistor. So we need, so the question is saying we need V output equals to VOH and V output equals to VOL when, this is when T is greater than 100 degrees Celsius, and this is when T is less than 100 degrees Celsius. So basically this comparator should go to higher saturation to high output when temperature becomes 100 degrees Celsius, and it remains low when it is less than 100 degrees Celsius. So how we will make the circuit? One more thing, the thermistor characteristics is like this. So this is temperature, this is resistance dropping. If we talk about then voltage, that is V T, that is this voltage VT. So once the resistance will be dropping, uh, then the voltage across that thermistor will also drop. So it is also like this. Okay. So this is the reason why, since the temperature is increasing, the voltage across the thermistor is decreasing. So if we analyze, if we maintain this point, this node A point at some potential, and once if we are increasing temperature, this potential, the potential at node B, that is V of T, reduces as the temperature is increasing. This B voltage reduces and become less than VA. Then what will happen? VA will be greater than VB at a temperature, let's say 101 degree Celsius. Temperature 101 degree Celsius. Okay, T equals to 101 degree Celsius. So VA will be higher than VB because VA is the voltage of temperature 100 degrees Celsius. You have maintained like that. And VB is the temperature, is the voltage at 101 degrees Celsius. Is the voltage at 101 degrees Celsius. So it will be reducing as the temperature is increasing for thermistor, the voltage will be reducing. So once this condition is achieved, so this condition is basically T greater than 100 degrees Celsius, then VA will be greater than VB, so our output will become VOH. Okay, VA will be greater than VB. Okay, so then output will be high. So that's what we want here. So, but the conditions when temperature is less than 100 degrees Celsius. So let's say for T equals to 99 degrees Celsius, and VA will be less than VB because VA is being set at 100 degrees Celsius and this is at 91 degrees Celsius. VB. Okay, that is the temperature across thermistor. So then VA is less than VB, then VO will be V output will be VOL. Okay, that is the lower threshold. Or the output will be at uh, lower saturation, negative saturation. So now we need this resistance at 100 degrees Celsius. So what it will be? We have the equation here. We have this equation. So I'll just write it down for you. So R of at T naught into e to the power b 1 by T minus 1 by T naught. Fine. So T naught is temperature of 25 degrees Celsius. So we have R of T naught as 100 kilo ohms. E to the power B we know that is 4000, and then we have temperature, we are talking about 100 degrees Celsius, and since this is in Kelvin, then this will be 373 kelvins minus 1 by, this is 25 degrees Celsius, that it will be 283 298, sorry, 298 Kelvin. So we have this equation that brings to us that R will be 6.75 kilo ohms at 100 degrees Celsius. The temperature of the thermistor will be 6.75 kilo ohms. Okay, I'll add just one paper. So it becomes 6.75 kilo ohm. Now we got this value. Now we have to decide R2, R3, R1. We have made the circuit. Now we have to decide R4, R2, R3, R1 what it will be. So since we have to maintain this VA voltage at a voltage which is equivalent to the voltage of thermistor at 100 degrees Celsius, because that is the cutoff point or the changing point for the comparator. So for that, if we can make R4 equals to 1 kilo ohm, R2 equals to R3 equals to 6.75 minus 0.5 kilo ohms equals to 6.25 kilo ohms. So for each arm, like this is our circuit, this is grounded, this is R4, here R4 is there, there it is R3, this is R2, this is R1, this is R thermistor. So we need this point, this is VCC, we need this point to be equal to the voltage at 100 degrees Celsius. So for that we need this branch to be 6.75 kilo ohms, this branch to be 6.75 kilo ohm, because this is also being given to the terminal, this is also, this will be 6.75 kilo ohm at 100 degrees Celsius, this should also be 6.75 kilo ohms. Okay, so and since this R4, if we consider 1 kilo ohm, so R2, R3 we can choose as 6.25 kilo ohms. So the ultimately this branch will be having 6.75 kilo ohms, this will be having 6.75 kilo ohms. R of T, the thermistor resistor will be also 6.75 kilo ohms. Then what will happen? So this voltage will be maintained at VCC by 2. Okay, this will be maintained VCC by 2, and this voltage once it achieves 6.75 kilo ohms, then this voltage will become less than VCC by 2 VB, we'll say. So VB will become less than VCC by 2. There the trip will happen, then this is the case when T will become 100 degrees Celsius, greater than 100 degrees Celsius, and we can like make a circuit V output equals to VOH. We can, yeah, either on the circuit or off the circuit based on this output. So this is how we realize the this thermistor using a comparator. We are switching off and on, and once if this voltage, this VB is less than this VC, this voltage VCC by 2, then yeah, but once if the temperature is less than 100 degrees Celsius, then this VB will be more than this VCC by 2. So in that case, V output will be VOL. Okay. So this was the question. So I think we don't have time to see this question, and yeah, there were two more questions, but yeah. So just go through again what we did today. So we talked about whatever we did in week 3. Then we came to week 4 topics. We talked about comparators, like how they operate. Then we talked about the applications of comparators, that is window detectors, in which inverting comparator, non-inverting comparators are there, and this window detector is basically a combination of inverting and non-inverting comparators. It uses two reference voltages. So this is how the circuit looks like and the waveforms. And then we move forward to op-amp comparator with positive feedback. So why we needed this positive feedback? We needed positive feedback because there was noise. Because of noise, we were having fluctuations at the output level. Then we saw the effect of introducing two reference voltages in the circuit, and we saw that how these two effect of two reference voltage can reduce the effect of fluctuations at the output. So here we saw that, and this the gap between the upper threshold and the lower threshold, we termed is a term that as noise band. And based on that, we made circuits. We realized circuits like inverting Schmitt triggers and non-inverting Schmitt triggers. We analyze those circuits, we analyze those transfer characteristics of these circuits, and then we talk about hysteresis voltages also. That is the width of this noise band. And then we solved some questions which were based on inverting Schmitt triggers, and then they were also based on non-inverting Schmitt triggers. And by changing the threshold voltages, by introducing reference voltages also, we saw circuits. By introducing diodes also, we see some circuits, we saw some circuits. And then we we talked about if what if the input is within the noise band, then what is the output. That also effect we saw. We get a constant DC voltage. Then we saw a practical example of how a comparator can be used to turn on and off a circuit. So here we use a thermistor circuit. We realize a thermistor circuit using LM39 type op-amp circuit, and then we we calculate the resistance of the thermistor at the tripping point, and based on that we decided the values of R3, R2, R4 with circuit. So yeah, that's all. So we'll meet on next session, that is next Tuesday, same time. Thank you.